All right, so now we're going to walk through some of the problems that you've been working for practice. So at this point, you should have already worked through these problems, and you're just using this to go over and make sure that you've done it correctly and checking your work and all of that. So this problem is a pretty straightforward freezing point depression problem. The difference is that it is not a aqueous solution, it's a benzene solution. So benzene is our solvent, and acetone is our solute. So we have 400 grams of benzene and 200 grams of acetone. We're going to start with our equation that the change in temperature of freezing is equal to the constant freezing times the molality. Which means, of course, we're going to have to calculate the molality. Thankfully, we have all the information we need for that. We have 400 grams of benzene and 200 grams of acetone. And for molality, we need moles of solute over kilograms of solvent. Right? So with the mass of each of those and the chemical equation for acetone, we can figure out moles and kilograms of solute and solvent. So when I calculated the molar mass of benzene, I got it to be 58.08 grams per mole. That's 3 times carbon, which is 12, plus 6 times hydrogen, which is 1.008, and 1 oxygen, which is 16. Added all that together, got 58.08 grams per mole, which means if we're starting out with 200 grams, and we set up our conversion factors here, that we are going to divide by 58.08 grams in 1 mole. The grams cancel, we're left in moles, and that came out to be 3.44 moles. Right, so that's our moles of solute. Then we needed to have kilograms of solvent. Well, we have 400 grams of benzene. We need to convert that into kilograms. There are 1,000 grams in 1 kilogram, so the grams cancel, and we're left with 0.4 kilograms of solvent in that case. So to get our molality, we're going to put 3.44 moles over 0.4, which comes out to a molality of 8.61. We use a little m to symbolize our molality. So then, now that we have the molality, we know the constant because it's given to us in the equation, we can figure out the change in freezing point. So the change in the temperature of freezing is equal to 5.12 times 8.61. And then from here, it's a really straightforward, easy math problem. We're going to multiply those two numbers together, and we get 44.1 is our change in freezing. And remember, freezing point is going to be depressed. So I like to just put a negative out there so that I know that it's going to go down. And that's 0 degrees Celsius. So a change in temperature of negative 44.1 degrees Celsius is the answer that I got there. All right, so these are another couple of questions that sort of go back to our different ways of calculating concentration. The first one is about molality, just sort of working with it in various directions. And the second one is about mole fraction. So these are both sort of review questions that we're going to go over now. So the first one is, how many grams of sodium bromide must be dissolved in 400 grams of water to produce a 0.5 molal solution? So we know we're working with molality, and we know that molality is equal to moles of solute over kilograms of solvent. And we know that we have a molality of 0.5, and we know that we have 400 grams of solvent, but we need that to be in kilograms, so we're going to convert that. Again, 100 grams are in a kilogram. Sorry, 1,000 grams are in a kilogram. I wrote it right, but I said it wrong. Grams cancel, and we end up with 0.4 kilograms. So we have 2 of our pieces of information. We're missing 1, the moles of solute. Of course, the question asks about grams, so that's something we're going to have to come back and be cognizant of later. But we can go ahead and plug in for now and solve for the one variable that we don't know. So we know that the molality is 0.5. And we know that we don't know the moles of solute, but we do know that there are 0.4 kilograms of solvent. So we end up with 0.5 equals x over 0.4. We multiply both sides by 0.4, and we get that 0.2 equals x. Now, x is going to come out in moles of solute, so that's 0.2 moles. And the question is asking about grams. So we have to convert those moles to grams. We're going to use the molar mass to do that, and it turns out that the molar mass of sodium bromide is 102.9 grams per 1 mole, right? And then we are going to cancel out our moles, and we have grams left. So that comes out when we do that, finish that conversion, comes out to be 20.58 grams. And we should only have 3 significant digits, so we're going to round that in a final answer to 20.6 grams of sodium bromide as our final answer for that question. And then as we move on to the next question, which is calculate the mole fraction of each component in a solution of 2.5 moles of ethanoic acid in 10 moles of water, then we remember that our mole fraction is essentially like a percent composition or something. It's the part over the whole with everything in moles, everything measured in moles, because it is the mole fraction. And because we have to do each component, we want one for the solute and one for the solvent. So we have ethanoic acid as our solute and water as our solvent. So if we use our acid first, we're going to set up that fraction. And this one's really easy because everything's already in moles. So we're going to put that 2.5 moles over the total number of moles in the solution, which isn't just 10, but is 10 plus 2.5, so 12.5. And that comes out to equal 0.2 as our mole fraction for the acid. And then we do the same thing for water. We're going to put the part of the solution that is water, which is 10 moles, over the whole solution, which again is all of the moles added together, so 12.5. And that comes out to be 0.8. Again, you can always double check that you've done these correctly when you're doing them for each component, because they should add up to 1, because they're essentially percents, just a part of the whole. So we get 0.2 as our mole fraction for the acid and 0.8 as our mole fraction for the water. And now we're back to a freezing point depression problem, except this one doesn't just ask what the difference in freezing point is. It actually asks what is the freezing point of a solution. So you have to apply that change to the original freezing point. But other than that, it's essentially the same question. You're going to start with your equation, which is that the change in your temperature of freezing is equal to your constant of freezing times your molality. You, of course, have to figure out your molality. So you're given that there are 12 grams of carbon tetrachloride and 750 grams of benzene. Again, we're going to remember that molality is equal to the moles of solute over your kilograms of solvent. Right, so we have to change everything into the proper units. This time I'm going to start with our solvent, which is benzene. We have 750 grams. We know that there are 1,000 grams in 1 kilogram, so that's 0.75 kilograms of benzene. We also know that we have 12 grams of carbon tetrachloride, and I figured out its molar mass to be 153.8 grams per mole. So we have 12 grams of carbon tetrachloride, and we're going to convert that into moles. 1 mole is 153.8, right? I got that by saying 12.01 plus 4 times 35.45, which is the molar mass of chlorine, all adds up to 153.8. And so that I get a total number of moles for carbon tetrachloride as 0.078 moles when I round it to 3 sig digs. Then we're going to plug that into the equation now that we have the molality. So the change in temperature of freezing is equal to 5.12 because that's the constant of freezing, times 0.078, which was our molality. It's not a very concentrated solution. It's a pretty dilute solution, so we're probably not expecting a big change in temperature here. And when we do that math, it comes out to be 0.399 degrees Celsius. Which is not a big change. And again, this is freezing point, so we know that freezing point gets depressed by a solute. Boiling point gets elevated, so this is a negative change. It's going to go down. And the question didn't ask what the change was. It actually asked what is the freezing point of the solution. So we know that benzene started with a freezing point of 5.48, and the solution, adding that solute, depressed it by 0.399 degrees Celsius. So we're going to subtract that, and we end up with a final freezing point of 5.08 degrees Celsius. And that would be our final answer. We have to actually subtract the change in temperature from the original freezing point. So then if we move on to the last questions that you had to practice, those were actually making dilution practices. So here's the work I did for this freezing point depression question. Notice that it is not just the same kind of straightforward question that we've done before. It's not asking what is the change in freezing point. It's actually asking for the new freezing point. So I set up our equation. The change in temperature freezing is equal to the constant of freezing times the molality. Of course, we had to figure out the molality, which we know is moles of solute over kilograms of solvent. So I took the 750 grams of benzene and converted it into kilograms, knowing that there are 1,000 grams in 1 kilogram, and got 0.75. Then I got the 12 grams and converted it into moles. Which it looks like I then plugged in as the molality, which is a mistake, so we'll have to fix that. Let's go through and just erase that, and let's fix that whole process. So I have the moles now at 0.078. So now I can figure out the molality, which is going to be the moles, 0.078, over the 0.75, which is going to come out to be... All right, so I'm just erasing the final answer portion of this so that we can fix that. So that's going to come out to be 0.104 molal solution. And we're going to plug that in to our equation. Our change in temperature of freezing is equal to 5.12 times 0.104, which comes out in the end to be 0.532, which we then have to subtract from our original freezing point, which is 5.48, and that gives us 4.95 degrees Celsius as our final answer. So now we have a making dilutions equation that you've been practicing. So we're going to start with our formula for this, which is M1V1 equals M2V2. Those are capital M, so that's molarity, remember, which is moles of solute over liters of solution. That's our molarity. And the question says, how could you prepare 250 milliliters of a 0.2 molar sodium chloride solution using a solution of 1 molar NaCl with water? So we know that the solution that we're starting with, our M1, is 1 molar. We don't know our V1. That's essentially the question. How can we make that? So how much do we need to use of the 1 molar solution? And we want to make a molarity 2 of 0.2 with a volume of 250 milliliters. So we have 3 of the pieces of information. We're only missing one of them, so we can just plug those into our equation. We're going to have 1x, or just x, is equal to 0.2 times 250, so that we end up with basically a really easy equation to solve here. X equals 50. when we do 0.2 times 250, and that's going to come out in milliliters because remember our volumes are going to be in the same unit. So if we use milliliters for one, the second one's going to come out in milliliters. And so that is our final answer, 50 milliliters of that 1 molar.